by Paul Parsons and Gail Dixon. Quercus. Image description. New York, London. Copyright 2014 Paul Parsons and Gail Dixon. All illustrations by Mark Franklin. All rights reserved. No part of this book may be reproduced in any form or by any electronic or mechanical means, including information storage and retrieval systems, without permission in writing from the publisher, except by reviewers, who may quote brief passages in a review. Scanning, uploading, and electronic distribution of this book or the facilitation of the same without the permission of the publisher is prohibited. Please purchase only authorized electronic editions, and do not participate in or encourage electronic piracy of copyrighted materials. Your support of the author's rights is appreciated. Any member of educational institutions wishing to photocopy part or all of the work for classroom use or anthology should send inquiries to Permissions C.O. Quercus Publishing Inc., 31 West 57th Street, 6th floor, New York, NY 10019, or to permissions@quercus.com. ISBN 978-1-62365-111-4 distributed in the United States and Canada by Random House Publisher Services C.O. Random House, 1745 Broadway, New York, NY 10019 www.quercus.com. Image description. Contents: the periodic table. Introduction. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, rubidium, strontium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon, cesium, barium, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, thallium, lead, bismuth, polonium, astatine, radon, francium, radium, actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium. The transfermium elements. Glossary. The authors. The periodic table. The periodic table shows the chemical elements ordered by atomic number of protons in the nucleus, but arranged in rows periods so that elements with similar chemistry occur in the same vertical column group. Here, elements with the same chemical and physical properties are shown by the color categories identified in the key at right. In general, members of each category also have a similar chemical valency, a measure of the number of bonds an element can form. Each element is represented by its chemical symbol. Above the symbol is the element's atomic number and below is the element's name. Image description. The entire periodic table. Element categories. Image description. Alkali metals. Image description. Alkaline earth metals. Image description. Lanthanides. Image description. Actinides. Image description. Transition metals. Image description. Post-transition metals. Image description. Metalloids. Image description. Other non-metals. Image description. Halogens. Image description. Noble gases. Image description. Unknown chemical properties. Image description. Alkali metals. This group 1 inch of metals occupies the far left column of the periodic table. They are all soft but solid metals at room temperature, and are highly reactive, for example, when dropped in water. Elements include Li, Na, K, Rb, Cs, and Fr. Image description. Alkaline earth metals. The alkaline earth metals are silver-white metals at room temperature. The name is a term that refers to the naturally occurring oxides of these elements. For example, lime is the alkaline oxide of calcium. Elements include B, Mg, Ca senior, Ba, and Ra. Image description. Lanthanides. The lanthanide elements occupy a horizontal strip normally appended at the foot of the periodic table. Named after lanthanum, the first element in the series, they are generally found in less common mineral rocks, such as monazite and bastnasite. Elements include La, C, Pr, Nd, Pm, Sm, Eu, Gd, Tb, Di, Ho, Tm, Yb, and Lu. Image description. Actinides. The actinides fill the second horizontal strip at the foot of the table. Named after their first element, actinium, they are all highly radioactive. So much so, that natural reserves of many of these elements have decayed away to nothing. Elements include AC, TH, Pa, U, NP, Pu, Am, Cm, Bk, Cf, S, Fm, Md, No, and Lr. Image description. Transition metals. The transition metals occupy a broad swath in the center of the periodic table. They are harder than the alkali metals, less reactive, and are generally good conductors of both heat and electrical current. Elements include Sc, T, V, crossing, Mn, Fe, company, Ni, Ku, Zn, Y, Zr, Nb, Mo, Tc, Ru, Rh, Pd, Ag, Cd, Hf, Ta, W, Re, Os, Ir, Part, O, Hg, Rf, D flat, Sg, Bh, Hs, and Cn. Image description. Post-transition metals lying in a triangular region to the right of the transition metals. The post-transition metals are soft metals that mostly have low melting and boiling points. They also include mercury, which is liquid at room temperature. Elements include Al, Ga, In, Sn, T, Pb, and Bi. Image description. Metalloids. The metalloid elements form a line between the metals and nonmetals in the periodic table. Their electrical conductivity is intermediate between the two groups, leading to their use in semiconductor electronics. Elements include B, C, J, As, Sb, Te, and Po. Image description. Other nonmetals. In addition to halogens and noble gases, there are other elements that are simply classified as other nonmetals. They display a wide range of chemical properties and reactivities. They have high ionization energies and electronegativities, and are generally poor conductors of heat and electricity. Most nonmetals have the ability to gain electrons easily. They have lower melting points, boiling points, and densities than the metal elements. Elements include H, C, N, O, P, S, and Se. Image description. Halogens. The halogens, known as group 17, are the only group to contain all three principal states of matter at room temperature: gas fluorine and chlorine, liquid bromine, and solid iodine and astidine, all nonmetals. Elements include F, Cl, bridge, I, and At. Image description. Noble gases. The noble gases are nonmetals occupying group 18 of the table. They are all gaseous at room temperature and share the properties of being colorless, odorless, and unreactive. Including neon, argon, and xenon, they have applications in lighting and welding. Elements include He, Ne, Ar, Kr, Z, and Rn. Image description. Unknown chemical properties. This is a label reserved for elements that can only be manufactured in a laboratory. Very often, only minute quantities of such elements have been created, making it impossible to ascertain their exact chemical classification. Elements include Mount, Ds, Rg, Ut, Fluid, Uop, Lv, Us, and Uo. Introduction. In the early 1860s, a Russian chemist working at St. Petersburg State University came up with an idea that would overturn our understanding of the chemical world. Dmitry Mendeleev put forward the idea of representing all of the known chemical elements in a table, according to their composition and properties. This insight not only enabled him to predict the properties of his yet undiscovered elements, but would also shape the course of chemical research forevermore. Mendeleev was fascinated by the chemical elements. Elements are the fundamental building blocks of chemistry, chemical substances that can exist as individual atoms as opposed to more complex chemical compounds, the smallest units of which, molecules, are made by joining atoms of different elements together. Mendeleev wondered if there was any way to order the elements according to their properties. He set about listing all the known elements. There were 62 of them at the time by what's known as their atomic mass number. An atom consists of electrically neutral neutron particles and positively charged protons clustered tightly into a central nucleus, around which orbits a cloud of negatively charged electrons. The mass of the electron particles is so small compared to the others that it's usually ignored. The neutrons and protons, however, are heavier. These particles weigh about the same as each other. Counting up the total number of neutrons and protons in an atom's nucleus yields a figure known as the atom's atomic mass number. Mendeleev arranged the elements in a long line, left to right, in order of their atomic mass. It was then that he noticed something strange. If he chopped this linear sequence into strips and arranged the strips into rows, to make a table, each column in the table tended to contain elements with similar properties. His left-hand column, for example, contains sodium, lithium and potassium, all of which are solids at room temperature, tarnish quickly and react violently with water. Because of this similarity, he referred to the columns of the table as groups of elements, while the repetition of properties led him to name the rows periods. He published his periodic table in 1869. Mendeleev firmly believed that elements should be grouped according to their properties. So much so, he made occasional tweaks to his table, shifting elements on by a column or two to place them in a group with other, more similar, elements. Doing so inevitably left gaps. As it turned out, though, these only served to reinforce the table's validity, by making it testable. Mendeleev asserted that the gaps corresponded to elements that were yet to be discovered. For example, arsenic should have occupied the slot in period 4, group 13. But Mendeleev believed it better fitted with the properties of elements in group 15, which was where he duly placed it. Sure enough, new elements gallium and germanium were later discovered that filled the missing slots in groups 13 and 14, and fitted the properties of those groups perfectly. In places, Mendeleev was so convinced that elements should be grouped by their properties that he even broke the rule of ordering by atomic mass. In so doing, he uncovered the true principle by which the elements are arranged, not by their atomic mass, but by a new property called atomic number. Whereas atomic mass is the total number of neutrons plus protons in the nucleus, atomic number is determined just by the number of protons it contains. Because protons each carry unit electric charge, atomic number is essentially a measure of the charge on the nucleus, as would be proven in 1913 by the British physicist, Henry Moseley. Atomic number also turns out to be equal to the total number of negatively charged electrons orbiting around the nucleus, making the atom's overall net charge zero. An element can be uniquely specified by its atomic number. For example, carbon is synonymous with element 6 inches and plutonium is element 94. Moseley's analysis enabled chemists to refine the table further and reveal more gaps, which suggested that there were more new elements waiting to be discovered, with atomic numbers 43, 61, 72 and 75. Scientists subsequently found these elements, now known as technetium, promethium, hafnium and rhenium, respectively. Despite Moseley's confirmation of the order of the chemical elements, there was still no real explanation for their periodic properties, why the elements in each group were so similar. It wasn't long, though, before the answer to that question would be discovered via an emerging branch of science known as quantum theory, which gave physicists new insights into the way subatomic particles interact with one another. When two substances react chemically, what's actually happening is that atoms and molecules of the substances are exchanging and sharing their electrons. Quantum theory determines the behavior of electrons. It revealed that the electrons in an atom are organized into a number of levels, also known as shells, each of which can accommodate a fixed number of electron particles. As you go from one element to the next, an atomic number increases, each shell gradually fills up, until it's full and the process repeats. Each of Mendeleev's periods corresponds to the filling of an electron shell. Each group has the same number of electrons in its outer, valence, shell, which is the principal determinant of chemical behavior. This is what gives the elements in the same group their similar properties. Not all electron shells in an atom can hold the same number of electrons. The innermost level, for example, can hold just 2. It is this that explains the large gap at the top of the periodic table, where hydrogen with just 1 electron in the valence shell occupies the far left-hand column, group 1, but helium, with just 1 extra electron, is in the far right column, group 18, amongst other elements that have a full valence shell. The similar gaps on periods 2 and 3 arise for the same reason. Conversely, the outer shells can hold an inordinately large number of electrons, which accounts for the existence of the lanthanide and actinide sequences, horizontal strips of elements that have been clipped out of the main body of the table and appended at the bottom for neatness. Although every atom of a given chemical element has a fixed number of protons in its nucleus, the number of neutrons can vary. Atoms with different numbers of neutrons are known as isotopes. Different isotopes of the same element generally have the same chemistry but different nuclear properties, such as half-life. See glossary. Other differences can occur from the way atoms are arranged in a substance. Pure carbon, for example, can take the form of soot, graphite and diamond. Such different forms of a chemical element are known as allotropes. In the text that follows, we meet all the chemical elements that have been discovered so far. There are 118 of them. Each of the first 100 has its own section. The heavier, transfermium, elements, of which there are 18 known beyond element 100, are rarer and have few applications, and so are detailed in a single consolidated section at the back of the book. Image description. H. Atomic number 1. Hydrogen. Image description. Atomic number 1. Category: non-metal. Atomic weight 1.00794. Melting point -259 degrees Celsius -434 degrees Fahrenheit. Color Na. Boiling point -253 degrees Celsius -423 degrees Fahrenheit. Phase: gas. Crystal structure Na. Image description. Hydrogen is the number 1 element of the periodic table and earns this status for a range of reasons. Along with helium and lithium, it was one of the first 3 elements produced during the Big Bang. It is the most abundant element in the universe, accounting for 88% of all atoms, and it is the lightest of all the elements, with only 1 proton, which is why it is number 1 in the periodic table, and 1 electron. Hydrogen is life-giving in a variety of ways. It is the fuel that keeps our sun and other stars burning. Every time you sunbathe or watch the beauty of a glowing sun. Image description. H. Atomic number 1. Hydrogen. Image description. Atomic number 1. Category: non-metal. Atomic weight 1.00794. Melting point -259 degrees Celsius -434 degrees Fahrenheit. Color Na. Boiling point -253 degrees Celsius -400 degrees Fahrenheit. Phase: gas. Crystal structure Na. Image description. Hydrogen is the number 1 element of the periodic table and earns this status for a range of reasons. Along with helium and lithium, it was one of the first 3 elements produced during the Big Bang. It is the most abundant element in the universe, accounting for 88% of all atoms, and it is the lightest of all the elements, with only 1 proton, which is why it is number 1 in the periodic table, and 1 electron. Hydrogen is life-giving in a variety of ways. It is the fuel that keeps our sun and other stars burning. Every time you sunbathe or watch the beauty of a glowing sunset, you are enjoying the result of a massive nuclear reaction. At the sun's core, the temperature is around 15 million degrees Celsius, 27 million degrees Fahrenheit, and the density is 200 kilograms per liter, 250 pounds per pint. In such conditions, hydrogen will begin to burn in a nuclear process and form helium nuclei, emitting huge amounts of energy. At standard temperature and pressure, hydrogen is a colorless and odorless gas that exists in the diatomic form H2, diatomic, meaning that it consists of 2 atoms. In this form, hydrogen is highly combustible and readily forms compounds with other elements. Combined with oxygen, hydrogen forms the water that fills the seas, rivers, lakes and clouds. Allied with carbon, it helps to bond the cells of living beings. Hydrogen is also abundant in the Earth's crust, in the hydrocarbons that have been formed from decaying organisms. These have become our modern-day fuels, such as crude oil and natural gas. Now scientists believe that hydrocarbons may also be formed in the deep earth, from methane that's subjected to extreme pressures and temperatures. Hydrogen is a key element in acids, and it was this aspect of its chemistry that led to its discovery. In 1766, Henry Cavendish, a wealthy British man with an interest in science, observed bubbles of gas rising from a reaction of iron filings in dilute sulfuric acid. He collected the gas and found it to be highly flammable and very light, qualities that made the gas seem unusual to Cavendish. He was also the first person to prove that when hydrogen burned it formed water, showing that water could be made from another substance and thus disproving Aristotle's theory that there were 4 basic elements, of which water was one. Image description. This reaction between pieces of zinc metal and hydrochloric acid produces bubbles of hydrogen. Hydrochloric acid molecules are made of hydrogen and chlorine atoms. The zinc is more reactive than hydrogen and replaces it to make soluble zinc chloride. Each hydrogen atom turfed out of the acid combines with another to form diatomic hydrogen gas. Hydrogen is lighter than air and as a result was used in balloon flight, which became popular during the 19th century, and in the airships that crossed Europe on scheduled flights in the early 1900s. During the First World War, Zeppelins were used for reconnaissance missions and bombing raids on London. Their light weight kept them out of the reach of fighter planes. The Hindenburg crash of 1937, when a Zeppelin burst into flames while attempting to land, ended the airship era, although this was not caused by a hydrogen leak, as assumed at the time. Today, around 50 million tons, 55 million tons of hydrogen are produced yearly, and large quantities go into fertilizer production. Nitrogen and hydrogen are used as part of the Haber-Bosch process, which uses natural gas and air to create ammonia, an important raw material in fertilizer production. Fritz Haber won the 1918 Nobel Prize in Chemistry for this discovery, and his colleague Carl Bosch won a Nobel Prize in 1931 for the development of high-pressure methods in chemistry. Hydrogen is the key element in the thermonuclear bomb, which produces sufficient explosive energy, through nuclear fusion between the hydrogen isotopes deuterium and tritium, to wipe out entire cities. Such weapons currently require a nuclear fission explosion, see uranium, to kickstart the fusion process. Research is now focused on producing a thermonuclear weapon that would not require a fission reaction to activate it. A process called inertial confinement fusion would use a high-energy laser beam to condense hydrogen to a temperature and density that would ignite a fusion reaction. Hydrogen's presence in water confirms its number 1 status on the periodic table. It also explains some of the strange chemistry behind water and ice. If you've ever wondered why ice cubes float in water, and vast swaths of ice float on the surface of seas and oceans, the answer lies in hydrogen. Solids are usually denser than liquids because, as most liquids cool, the molecules slow down and get closer together as they eventually form a solid. This tends to make solids denser than liquids, so you'd expect ice to sink in water. However, as water cools down to 4 degrees Celsius (39 degrees Fahrenheit) and the molecules slow down, hydrogen bonds occur, which allow one water molecule to link with 4 other water molecules. This creates an open, crystalline lattice where the molecules are spread out and less dense in a given space. Hence, ice is less dense than water and will float on its surface. There's a similar explanation behind the annoyance of burst pipes in winter. If the water temperature is really low, the latticework of molecules in the ice makes it expand, and the resultant buildup of pressure against the sides of the pipe causes it to burst. This is why it's important to keep your heating on low during winter, even if you're going away, and to insulate pipes that are in attics or close to external walls. Water vapor is the invisible gaseous state of water and is particularly important for regulating temperature on Earth. As a potent greenhouse gas, water vapor regulates the temperature of Earth so that it is warm enough to support human, animal and plant life. It is removed from air via condensation and replaced by evaporation and transpiration, water loss from plants. It's a key aspect of Earth's water cycle and is vital for the formation of clouds and precipitation, rain, sleet and snow. Water vapor explains why dew forms on plants and why delicate silk draperies of spiders' webs become noticeable in the morning after a cold, foggy night. As the exposed surface cools down, water vapor condenses at a rate greater than it can evaporate, which results in the formation of water droplets. If temperatures are low enough, dew will become the icy breath of Jack Frost. Image description. This striking mushroom cloud was produced by the detonation of Castle Romeo, an 11 megaton thermonuclear bomb, on March 26, 1954. Thermonuclear, or fusion, bombs contain isotopes of hydrogen that are fused together by great heat, which is normally generated by a smaller nuclear fission explosion. The fusion process releases vast amounts of energy locked away inside the nuclei of atoms. Image description. He, atomic number 2. Helium. Image description. Atomic number, 2. Category, noble gas. Atomic weight, 4.002602. Melting point, minus 272 degrees Celsius minus 458 degrees Fahrenheit. Color, Na. Boiling point, minus 269 degrees Celsius minus 452 degrees Fahrenheit. Phase, gas. Crystal structure, Na. Image description. Helium is named for the Greek god of the sun, Helios, after it was first detected as unknown yellow spectral lines in sunlight. In India in 1868, French astronomer Jules Janssen passed sunlight through a prism during a solar eclipse to split the light into its component colors. He found a sudden jump in the brightness of yellow light, which he initially believed to be caused by sodium. The same year British astronomer Norman Lockyer and chemist Edward Frankland observed the same yellow line in the solar spectrum while sky-gazing over smoky London. Lockyer caused controversy at the time by claiming that it was a new element present in the Sun. He had the last laugh, however, when his hypothesis became accepted within the scientific community. Lockyer also chose the element's name. Along with hydrogen and lithium, helium was formed during the Big Bang. It is the second most abundant element in the universe after hydrogen, making up 23% of its matter. On Earth, helium is present in some minerals, but most of it is sourced from natural gas. Helium is a member of the noble gases group 18 of the periodic table, which are odorless, colorless, have very low chemical reactivity and have molecules consisting of a single atom. The group gains its noble name because the gases do not bond with other riff-raff elements. The reason for this is that their outer shell of electrons is full, giving them little tendency to react chemically. One of helium's key uses is in cryogenics, most notably in the cooling of superconducting magnets in MRI scanners. Liquid helium at a temperature of -269 degrees Celsius (452 degrees Fahrenheit) cools the magnets used to create the intense magnetic field required. Radio waves within the magnetic field interact with hydrogen atoms and water and other molecules in the body in order to produce an image that enables doctors to identify tumors and other medical problems. Being lighter than air, helium is used in airships and balloons. Helium has also been used as a medium to force rocket fuel and oxidizers out of their storage tanks and to actually make rocket fuel by using the low temperature of liquid helium to condense hydrogen and oxygen into liquid form. It is also used to purge fuel from spacecraft launch gantries to prevent them from igniting dangerously during liftoff. The Saturn V booster used in the Apollo program required 400,000 cubic meters (13 million cubic feet) of helium to launch. One of helium's isotopes, helium-3, has sparked considerable interest as a potentially safe, environmentally friendly fuel. While it's scarce on Earth, it's plentiful on the Moon, which adds weight to the argument for a NASA moon base. One of the space agency's goals is to mine the Moon for fuel to be used in fusion reactors, futuristic power plants that would produce no carbon dioxide, thus reducing damage to the environment, and helium-3 is considered a possible fuel for such reactors. Image description. A gas discharge lamp filled with helium gives off a ghostly purple glow. Electric current ionizes the gas, tearing electrons from their host atoms and permitting a current to flow through the gas, causing it to glow. Image description. Li, atomic number 3. Lithium. Image description. Atomic number 3. Category: alkali metal. Atomic weight 6.941. Melting point 181 degrees Celsius (358 degrees Fahrenheit). Color: silver white. Boiling point 1342 degrees Celsius (2448 degrees Fahrenheit). Phase: solid crystal structure, body centered cubic. Image description. Image description. Along with hydrogen and helium, lithium is one of the three elements to be created during the Big Bang. Under standard conditions, this soft, silvery white alkali metal is the lightest of all metals and the least dense solid element. Lithium is highly reactive and has to be stored with a coating of petroleum jelly. Lithium carbonate has been life-changing for thousands of people across the world. In the 1940s, electroconvulsive therapy and lobotomy were considered standard treatments for people with mental health issues. Such extremes were to come to an end for many in 1949 following the work of Australian Dr. John Cade, a senior medical officer in the Victoria Department of Mental Hygiene, who discovered that when guinea pigs were given lithium carbonate, these normally highly strung animals became so placid that they would lie on their backs contentedly for hours. Cade experimented by taking lithium himself before giving it to one of his patients, who had been in the secure unit for many years. Within a few days the patient was transferred to a standard ward and a few months later he returned home and took up his old job. Other patients with mental health issues responded well to lithium carbonate, but toxicity was a problem in the early days. More than 10 milligrams of lithium per liter of blood can lead to mild lithium poisoning, and levels above 20 milligrams per liter can be fatal. Dosage levels are adjusted according to patients' needs so that the level of lithium in blood plasma is between 3.5 and 8 milligrams per liter. Within 10 years of Cade's findings, lithium was widely used to treat patients across the world. Little is understood of how lithium carbonate can help to smooth out the highs and lows that patients with bipolar disorder experience. It is thought, however, to reduce levels of a chemical messenger that can be overproduced in the brain. Intriguingly, the therapeutic powers of lithium may have been discovered as early as the 2nd century, when the physician Cyranus of Ephesus treated patients with mania and melancholia. He used the alkaline waters of his town, which we know contained high levels of lithium. The metal itself was first identified by Johann August Arfvedson, who detected the presence of a new element while working on petalite ore in 1817. Lithium's main ores today are spodumene, petalite and lepidolite. Large deposits of spodumene have been found in South Dakota in the United States of America (USA), as well as in Russia, China, Zimbabwe and Brazil. Lithium is also extracted from the brines of lakes, most notably those in Chile and California and Nevada in the USA. Despite its reactivity, lithium is useful in many everyday items. Lithium oxide is used in heat-resistant glass and ovenware, while lithium-ion batteries pack considerable power into small spaces and so are ideal for pacemakers, watches, laptops and cameras. Lithium is also important in the construction of airplanes. It combines with aluminum to form an alloy that's lighter than pure aluminum, thus reducing fuel consumption. Image description. Samples of the alkali metal lithium, which is soft enough at room temperature to be cut with a knife. Lithium has applications in areas ranging from battery technology to mental health medication. Image description. B. Atomic number 4. Beryllium. Image description. Atomic number 4. Category: alkaline earth metal. Atomic weight 9.012182. Melting point 1287 degrees Celsius 2349 degrees Fahrenheit. Color: silvery white. Boiling point 2569 degrees Celsius 4476 degrees Fahrenheit. Phase: solid crystal structure, hexagonal. Image description. Image description. Beryllium is the 4th lightest element, but it is not very abundant in the universe because it is only generated during supernova explosions. The element is named after beryllo, a Greek word meaning beryl, a mineral ore that contains beryllium. Bertrandite is another. Sometimes huge crystals of the mineral are discovered, some up to 6 meters 20 feet long, and the key areas for ores are in the USA, Brazil, Russia, India and Madagascar. One of its isotopes, radioactive beryllium-10, is generated when cosmic rays react with oxygen, and this has been detected in ice cores in Greenland. The Romans and ancient Egyptians prized emeralds and beryl, and the Roman writer and philosopher Pliny the Elder, writing in the 1st century AD, observed that they were both derived from the same mineral. It was not until the late 18th century that chemists in France noticed a previously unknown element in beryl ore, and the new element beryllium was successfully isolated in 1828. Beryllium is a lightweight, silvery white metal. It has no known biological role and it is toxic to humans. If beryllium fumes are breathed in, they cause a persistent lung condition called berylliosis, which includes symptoms such as inflammation of the lungs and shortness of breath. Workers exposed to beryllium alloys in the mid-20th century were most at risk, when early fluorescent lamps were coated with phosphors containing beryllium oxide. Manufacture of this lamp was ended when large numbers of workers at a plant in the USA contracted the lung disease. Beryllium has been key in the development of atomic theory because of the role it played in the discovery of the neutron. In the early 20th century, physicists believed that, due to measurements of atomic mass, nuclei must contain particles other than positively charged protons. British physicist Sir James Chadwick spent a decade exploring this field of atomic theory and, in 1932, discovered that if beryllium was bombarded with alpha rays from radium, it would emit an unknown subatomic particle. This particle had about the same mass as a proton but no electrical charge. Chadwick had discovered the neutron and, in 1935, received the Nobel Prize in Physics for his discovery. If a few % of beryllium is alloyed with copper, it forms a non-sparking, high-strength metal that is ideal for tools used in environments such as oil wells or where there are flammable substances and just one spark could spell disaster. Beryllium is a strong metal, which is lightweight, resistant to corrosion and melts at a very high temperature. All these factors combined make it ideal for use in spacecraft and missile components. Beryllium is also used in the windows of X-ray tubes because it is transparent to X-rays. The element is unusual in its ability to reflect neutrons, which is one reason why it is used in nuclear weapons. Inside the warhead, neutrons bombard uranium in order to release energy. As the neutrons are reflected back and forth contained by the beryllium casing, this increases the rate of the nuclear reaction within the weapon. Image description. The alkaline earth metal, beryllium. Although X-rays stream through it as if it were made of glass, this metal is highly reflective to neutron particles, leading to its use in nuclear weapons. Image description. B. Atomic number 5. Boron. Image description. Atomic number 5. Category: metalloid. Atomic weight 10.8111. Melting point 2076 degrees Celsius 3769 degrees Fahrenheit. Color: varied. Boiling point 3927 degrees Celsius 7101 degrees Fahrenheit. Phase: solid. Crystal structure: rhombohedral as boride. Image description. Image description. Boron is one of the unsung heroes of the periodic table. It may lack the glamour of gold or platinum, and have the dullest of names, but it can conjure intriguing chemical wizardry, and its compounds have proved useful for centuries. Boron is a key element in borax, also known as sodium borate, sodium tetraborate or disodium tetraborate. This is a salt of boric acid, which usually occurs as a white powder and dissolves easily in water. It has been used as a detergent, fungicide and pesticide for millennia, and also as a fire retardant, a component in ceramics, and as a flux to make molten metal easier to work. The name boron is derived from the Arabic barak, meaning borax. The salt was first discovered in Tibet and transported west via the Silk Road, an ancient trade route that linked China with the West to the Near East and Europe. Borax even gets a mention in the prologue of the English poet Geoffrey Chaucer's Canterbury Tales, written in the late 14th century. Borax was later used as a cosmetic and was mixed with oil, powdered eggshell and other ingredients to create the virginal white look favored by England's Queen Elizabeth I. The presence of boron itself was first noticed in 1732 as an unusual green flame by the French chemist, Geoffroy the Younger. This can be achieved by treating borax with sulfuric acid to change the boron into boric acid. Alcohol is then added and the acid is set alight. In 1808, British chemist Sir Humphry Davy tried to isolate pure boron from borate by heating it with potassium metal. In Paris, Joseph Louis Gay-Lussac and Louis Jacques Thenard were following the same procedure, but neither they nor Sir Humphry could isolate the pure element. It wasn't until 1892 that Ezekiel Weintraub of the American General Electrical Company sparked a mix of boron chloride vapor and hydrogen. Boron is only found as borate minerals on Earth. Large deposits of borates have been located in California's Death Valley, in the USA, and also in Tuscany, Italy. Today, it is mined mostly in the USA, Turkey, Tibet and Chile. Several allotropes, different forms of boron, exist. The most common is amorphous boron, a dark powder that reacts with metals to form borides but does not react with oxygen, water or acids and alkalis. Intriguingly, if boron is combined with nitrogen, the crystals produced boron nitride are almost as hard as diamond. These are much cheaper to create and have greater heat resistance, which makes them highly useful abrasives in steelworking. In industry, abrasives are used for cleaning, removal of excess material, sharpening and cutting. If you have some silly putty, also known as thinking putty, on your desk, you might find it interesting to know that boron crosslinks the polymers that give these colorful, silicone-based splodges their ability to be both soft and malleable in the hand but bouncy and hard when chucked around. Try it, it might help when considering the magnitude of the next element of the periodic table, the behemoth that is carbon. Image description. A sample of pure, crystalline boron. You won't find anything like this in nature, though, as boron only exists naturally in the form of compounds with other elements, such as the minerals kernite and colemanite. Image description. C. Atomic number 6. Carbon. Image description. Atomic number 6. Category: nonmetal. Atomic weight 12.0107. Melting point Na. Turns to vapor, sublimes before it melts. Color: clear diamond and black graphite. Sublimation point 3642 degrees Celsius 6588 degrees Fahrenheit. Phase: solid. Crystal structure: hexagonal graphite and face-centered cubic diamond. Image description. Image description. Carbon is one of the most important elements in the periodic table, at least for us here on Earth, its rich spectrum of chemical compounds make it the backbone of life on our planet. Carbon helps to power the nuclear reactions in the sun that provide us with light and warmth, and it is also a key component of our technology, integral to the fuel that powers civilization, the materials in our buildings, and even the clothes on our backs. Carbon is an element from antiquity, known to the ancient Egyptians and Sumerians as far back as 3750 BC, who used it for processing ores in the manufacture of bronze. Later, it would find another application in metallurgy, as the element used to convert raw iron into a super strong alloy, steel. The name, carbon, derives from the Latin carbo, meaning charcoal. Several different forms of carbon were known to the ancients, such as charcoal, coal and graphite, but it wasn't clear to them that these substances were just different facets of the same thing. This was established chemically in the 18th century. In 1779, German-Swedish chemist Carl Wilhelm Scheele showed that graphite contained carbon. 7 years later, a French team showed that graphite was, in fact, made mostly of carbon. Carbon is the 15th most abundant element in the Earth's crust. The planet's biosphere alone is home to 2,000 billion tons of the stuff. Carbon is a tetravalent atom, able to bond with up to 4 other atoms simultaneously, enabling it to form over 20 million different chemical compounds. This diversity is central to carbon's role at the heart of life on Earth. This is described in part by the carbon cycle, which governs how carbon is taken in by plants through photosynthesis from carbon dioxide in the atmosphere and then ingested by animals, before being returned to the atmosphere when these life forms ultimately die. Current environmental concerns hinge on the fact that a great deal of carbon is being added to the cycle by the digging up and burning of fossil fuels. The carbon in these substances, such as coal and oil, is turned into carbon dioxide when burned. In the atmosphere, this gas acts to trap heat from the sun, warming the planet. Carbon has many uses. As well as being used in steelmaking, it is the basis of plastics, cotton and linen. Carbon in its form as charcoal was also a key ingredient in the first practical explosive, gunpowder. Carbon comes in various different allotropes, which are essentially different substances formed by arranging the carbon atoms in different ways. Graphite is an allotrope made from sheets of bonded carbon atoms. The gemstone diamond, however, has a rigid interlocking lattice of atoms, formed at a high temperature and pressure. Most recently, an extraordinary form of carbon known as a fluorine has been discovered. Fluorines consist of graphite rolled into cylinders, nanotubes, or spheres known as buckyballs. They are hundreds of times stronger than steel. Image description. 2 forms of carbon, a graphite rod and industrial diamonds. These are known as allotropes of carbon, the same atoms just arranged in different ways. Image description. N, atomic number 7. Nitrogen image description. Atomic number 7 category, non-metal atomic weight 14.000672 melting point, minus 210 degrees Celsius minus 346 degrees Fahrenheit color, non-boiling point, minus 196 degrees Celsius minus 320 degrees Fahrenheit phase, gas crystal structure, Na image description. It's incredible to think that 78% of our atmosphere is made of the element nitrogen. Earth's abundance of nitrogen was caused by volcanic outgassing early in its history. By comparison, the element makes up just 2.6% of the atmosphere on the planet Mars. Nitrogen was discovered in 1772 by the British chemist Daniel Rutherford. In the 1760s, scientists Henry Cavendish and Joseph Priestley carried out experiments in which they removed all the oxygen from air. Quite what was left no one knew. It was their compatriot Rutherford who realized that the gas was a new element, subsequently named nitrogen. The name comes from the Greek words nitron and genes, together meaning niter forming. Niter was then the name for saltpeter, or potassium nitrate, the major component of gunpowder. Nitrogen-based compounds crop up frequently in the history of explosives. That's because they tend to want to release their nitrogen back into gas form extremely rapidly, along with a large quantity of heat. Nitroglycerin is made by reacting nitric acid with glycerin to produce an explosive liquid detonated by impacts. Invented in 1846, it was the first high explosive. Alfred Nobel invented dynamite in 1866 by absorbing nitroglycerin into kieselguhr, a soft powdered sedimentary rock, to create a much more stable explosive. The fortune he made from dynamite funds the prizes that now bear his name. Ironically, one nitrogen-based explosive, called azide, has saved many lives through its use in car airbags. An accelerometer detects the impact and detonates the charge with an electrical pulse, filling the bag with gas in 25 thousandths of a second. It is estimated that between 1990 and 2000, airbags saved more than 6,000 lives in the USA alone. Nitrogen is also a useful, inert, atmosphere that prevents damage caused by oxygen. For example, a piece of fruit stored in a sealed but non-refrigerated box of nitrogen will keep for up to 2 years. Liquid nitrogen is an effective coolant, often used for freezing blood and transplant organs. It also forms the basis of hydrazine, rocket fuel and widgets in canned beers, which release a surge of nitrogen gas to froth up the beer. The human body is 3% nitrogen by mass, incorporating the element into proteins, neurotransmitters and deoxyribonucleic acid DNA. The compound nitrous oxide N2O, laughing gas, is the gas in the anesthetic, gas and air, offered to pregnant women during labor. Nitrogen is also an essential nutrient for plants, and most plants take it in through their roots rather than taking it directly from the air. Nitrogen from dead organisms enters the soil, much of which is then consumed and released as gas by bacteria. Recognizing plants' need for nitrogen has been important for agriculture. In 1909, German chemist Fritz Haber came up with an efficient way to make ammonium nitrate fertilizer to enrich land on which crops are grown. In the last 20 years, these chemicals have doubled crop yields worldwide and are directly responsible for feeding a third of the planet's population. Image description. At some restaurants, diners can eat food that's been poached in liquid nitrogen before their eyes. Nitrogen only exists in its liquid state at temperatures below -196 degrees Celsius -320 degrees Fahrenheit. Image description. O. Atomic number 8. Oxygen. Image description. Atomic number 8. Category: nonmetal. Atomic weight 15.9994. Melting point -219 degrees Celsius -362 degrees Fahrenheit. Color: colorless. Boiling point -183 degrees Celsius -297 degrees Fahrenheit. Phase: gas. Crystal structure Na. Image description. Oxygen has been one of the most essential elements in mankind's evolution. It is the most abundant element on Earth, constituting half of the mass of the planet's crust and 86% of the mass of the oceans. It is also the third most abundant element in the universe, after hydrogen and helium, although our planet is unusual in the solar system for having such a high level of oxygen gas. Oxygen is highly reactive and will form oxides with most other elements, apart from helium and some of the inert gases. At standard temperature and pressure, two oxygen atoms combine to form O2, the colorless, odorless gas that makes up around 21% of air and is vital for almost all forms of life on Earth. To understand fully oxygen's life-giving role on Earth, we have to journey back 3 billion years, when changes in oxygen levels triggered the move toward biodiversity. It was at this point that blue-green algae started to develop and photosynthesis began. This is the process by which plants use carbon dioxide and light in order to produce energy. Oxygen is released into the atmosphere as a result. For around 1 billion years, most of the extra oxygen produced went into the oxidation of iron. Around 500 million years ago, as land plants began to grow, atmospheric oxygen reached the level of around 21% volume, where it has remained ever since. That rise in atmospheric oxygen enabled biodiversity because multicellular organisms, and higher life forms such as human beings and animals, require oxygen to thrive. Thus oxygen not only sustains human life on Earth, it also helped to create us in the first place. Oxygen's discovery can be attributed to 3 18th-century chemists, although around 300 years earlier, Leonardo da Vinci noted that air contained something vital for human and animal life and that without it a candle flame could not burn. In 1772, Swedish chemist Carl Wilhelm Scheele, see also carbon, became the first scientist to isolate oxygen by heating mercuric oxide and a number of nitrates. However, his discovery was not published until 5 years later. In the meantime, British chemist Joseph Priestley had produced oxygen by thermal decomposition of mercuric oxide and published his findings in 1774. He informed the chemist Antoine Lavoisier of his discovery, and the Frenchman became the first scientist to grasp the great importance of oxygen in chemical processes on Earth, respiration and combustion. As a result, scientific theories that had stood for 100 years were overturned. Lavoisier believed mistakenly that all acids contained oxygen, so he named the element oxygene, oxy meaning sharp, and gen meaning producing. Although erroneous, the name stuck and passed into common usage. Oxygen is required by almost every cell in the body for a number of reasons, including metabolism, growth of new tissue, and disposal of waste matter. If the brain is deprived of oxygen for a few minutes, its cells will start to die. After we inhale, oxygen in the lungs is picked up by the iron atom in hemoglobin, a protein found in red blood cells, and carried around the body to organs and tissue. Oxygen is a component of DNA and almost every other biological compound. It comprises 60% of the mass of human beings, because so much of our body is made up of water, which is a hydrogen-oxygen compound. It's in our bones and teeth and in our blood, sweat and tears. Image description. Oxygen in water. The colder the water is, the more dissolved oxygen it can hold. This is why you will sometimes see bubbles forming on the inside of a glass of tap water. As the water warms up, some of the oxygen it holds is forced out of solution. While being essential for life on Earth, oxygen is also responsible for forms of decay, such as food spoilage. Oxygen is tasteless, colorless, and has no smell, so it's easy to overlook it as a factor. However, the oxygen in air provides ideal conditions for the growth of microorganisms, molds and yeast, which feed and grow on the surface of foods. Also, oxidizing enzymes found in food speed up the chemical reactions between oxygen and that food, making it go off. Oxidation itself can also cause food to spoil because when fats oxidize, compounds are formed that produce a very strong, rancid odor. Mankind has developed many resourceful forms of preservation, from burying food in the ground, to keep it at a low temperature and help protect it from air, to drying, curing, canning, bottling, freezing, and vacuum packing. The percentage of oxygen in the air is constant up to an altitude of about 21 kilometers 13 miles. However, as altitude increases, air density decreases, which means that there are fewer oxygen atoms the higher you go. This results in altitude sickness, the symptoms of which include dizziness, nausea, headache, and exhaustion. The condition can be fatal, due to fluid buildup on the lungs or the brain. Mountaineers and skiers who spend time at high altitudes are careful to acclimatize to their surroundings, ascending the tallest peaks slowly and increasing altitude by no more than 300 meters 1,000 feet per day. Most cases of altitude sickness occur at heights of 3,500 meters 11,500 feet and above. The summit of the highest mountain in North America, Mount McKinley, also known as Denali, in Alaska, is at 6,194 meters 20,322 feet above sea level. Mount Everest, in Nepal, is 8,848 meters 29,029 feet above sea level. Apart from O2, the other main allotrope of oxygen is ozone, which consists of 3 oxygen atoms bonded together. In the stratosphere, 20 to 40 kilometers 12 to 25 mi above Earth, the ozone layer provides a protective shield for Earth from the sun's damaging ultraviolet rays. Some chemical pollutants destroy ozone, and so weaken the protective shield it provides. These pollutants include emissions from vehicle exhausts, industrial facilities, and fossil fuel power stations. In the lower part of the atmosphere, however, ozone itself is a pollutant, formed by chemical reactions between oxides of nitrogen and volatile organic compounds in sunlight. Breathing ozone can cause chest pain, coughing, and congestion. It can also worsen asthma and bronchitis. Oxygen gives us life, but we have used it in such a manner that it could make life on Earth highly dangerous for mankind. Its reactivity has been essential in the process of combustion, fueling factories and motor vehicles, and thus increasing carbon dioxide emissions and global warming. It took billions of years for oxygen levels to rise to enable biodiversity and the birth of mankind. It has taken just 300 years of industrialization to trigger a more dangerous turn in the planet's ecological course. Image description. Red blood cells are used by the body to transport oxygen from your lungs, where it is absorbed from the air, to your organs, where it gets put to work in biochemical reactions that generate energy. Disgraced cyclist Lance Armstrong, and other dishonest endurance athletes, are believed to have taken a substance called erythropoietin, which boosts red blood cell production, enhancing the oxygen-carrying capacity of the blood and making more energy available to the athlete's muscles. Image description. Atomic number 9. Fluorine image description. Atomic number, 9 category, halogen atomic weight, 18.998403 melting point, minus 220 degrees Celsius minus 364 degrees Fahrenheit color, pale yellow boiling point, minus 188 degrees Celsius minus 307 degrees Fahrenheit phase, gas crystal structure, Na image description. Fluorine is one of the most reactive and dangerous of the elements. Exposure to this pungent gas at just 0.1% of air for a few minutes can be lethal, and if a stream of fluorine is directed at almost anything, even a pane of glass or a brick, it will erupt into flames. Fluorine is a member of the halogen group of the periodic table, along with chlorine, bromine, iodine and astatine, and all share the characteristic of being highly reactive. In the 1520s, it was noted that the mineral fluorspar calcium fluoride would melt and flow when heated in a fire. Fluorine's name comes from the Latin fluor, meaning to flow. This led to its use as a flux. When added to furnaces, it would make the metallic smelt more fluid and therefore easier to work with. Alchemists realized that fluorides contained an as yet unidentified element, which was similar to chlorine. Isolating it proved a huge risk. However, due to its toxicity, a number of chemists died trying to do so and were dubbed the fluorine martyrs. In 1886, French chemist Henri Moissan was able to obtain fluorine through electrolysis. He was awarded the Nobel Prize in Chemistry in 1906 for this work. Fluorine may be reactive and dangerous in its natural state, but it is stable as fluoride, the form in which it is encountered naturally. Fluoride is considered essential for humans, although it is required in very small amounts. Approximately 3 mg (0.0001 ounces) a day is sufficient. In 1945, water fluoridation began in some areas of the USA, after scientists noted that people who lived in areas with higher water fluoride levels had fewer dental cavities. The fluoridation of water is standard practice in many countries. Levels of fluoride have to be closely monitored, however, because exposure to high levels can lead to skeletal fluorosis, where fluoride accumulates in the bones and leads to deformities. The U.S. Environmental Protection Agency has set a maximum amount of fluoride in drinking water of 4 mg per liter. Fluoride is added to toothpaste because when it is applied to teeth it forms crystals that make enamel more resistant to acid, which can ordinarily make the tooth surface porous and prone to decay. The most resilient fluorine compound has become a byword in modern times, Teflon, or polytetrafluoroethene if you want to know its chemical name. Teflon was discovered in 1938 by Roy Plunkett at DuPont Research Laboratories, New Jersey, USA, who was researching new chlorofluorocarbon refrigerants. Plunkett had stored polytetrafluoroethylene gas in small cylinders for chlorination and on opening one of these cylinders, found a white powder, which he decided to test. The substance was a plastic that was heat-resistant, chemically inert and remained flexible down to minus 240 degrees Celsius minus 400 degrees Fahrenheit, which made it useful for use on space flights. Another property of the compound was that nothing would stick to it, which led to its use as a coating to create non-stick saucepans. Teflon is also used in breathable clothing, which allows water vapor out but resists liquid water getting in. Image description. A fluorite crystal, a kind of mineral made of the compound calcium fluoride. Fluorite samples are often fluorescent, meaning that they give off light. Indeed, this mineral is the origin of the word. Image description. Ne, atomic number 10. Neon image description. Atomic number, 10 category, noble gas atomic weight, 20.1797 melting point, minus 249 degrees Celsius minus 415 degrees Fahrenheit color, colorless boiling point, minus 246 degrees Celsius minus 411 degrees Fahrenheit phase, gas crystal structure, Na image description. What would the Las Vegas Strip be without the glitz, glamour or indeed gaudiness supplied by neon light? What would Piccadilly Circus in London, or Times Square in New York, look like after dark without their glowing beacons and signage? Neon may be a traverse, using spectroscopy analyzing the light produced when an element is heated. Ramsay and Travers chilled air until it became liquid, then warmed it and captured the gases as they evaporated. After nitrogen, oxygen and argon were removed, they examined the tiny amount of gas remaining. On heating it, they saw astonishing spectral lines and said of the discovery, "The blaze of crimson light from the tube told its own story. Nothing in the world gave a glow such as we had seen. Neon produces only a reddish-orange glow and no other color." Ramsay's son, Willie, wanted to name the discovery novum, from the Latin word meaning new. His father liked the idea but preferred the Greek word for new, neos, hence the